Hello, and welcome to Differential Equations. This is lecture 24, Variation of Vector Parameters. Last time, we started talking about systems of ODEs. This time, we're going to talk about variation of parameters for vector-valued functions. So, just as when we were working with linear ODE for scalar-valued functions, if we know the general solution of a homogeneous linear ordinary differential equation for a vector-valued function, then we can use variation of parameters to find the general solution of any associated non-homogeneous equation. One simplification we discussed last time is that by introducing new variables if necessary, we can assume that the ordinary differential equation we're looking at is first order. Thus, we're interested in equations of the form dv dt equals a of t times v plus f bar of t, where v bar and f bar are valued in vectors with n entries, and A is valued in matrices of size n by n. Okay, so before we talk about variation of parameters, we should talk about the homogeneous case. So we need to recall some facts from last time. About homogeneous equations. Let's start with a simple example. So suppose we want to find all solutions of the equation x prime y prime equals multiplication by the matrix 2, 1, 0, 5 times xy. Right? So here our matrix A is constant. It doesn't depend on t. Right? If we write this out as two equations, the first equation, you do the matrix multiplication, you get x prime equals 2x plus y, and y prime equals 5y. Right? What makes this example simple is that we can solve the second equation for y. And then substitute into the first equation. Right, so this is simple because this ended up being a very easy equation. If this coefficient had not been 0, then both x prime and y prime would depend on both x and y, and we'd need to do something more complicated to solve it. But in this case, this is easy enough to solve. We have y prime equals 5y. So that tells us that y is equal to some arbitrary constant times e to the 5t. Okay. Now I'm writing the arbitrary constant as a lowercase b, and that's because it's the constant from the second equation, and I'm going to write the constant from the first equation as lowercase a. So that's why I'm choosing little b for this one. If we substitute this into the first equation, then we have x prime is equal to 2x plus little b times e to the 5t. Right? And perfect. So now this equation only depends on x and a forcing term. This forcing term has a arbitrary constant b, but that's okay. You just work with it. And we know how to solve this equation. You find a particular solution and then add the solution of the associated homogeneous. In this case, the particular solution would be b over 3 times e to the 5t. And the general solution of the associated homogeneous is little a times e to the 2t. Okay, hence the general solution is x of t, and I'm going to put the terms with an a first. So e to the 2t times a plus 1/3 e to the 5t times b, and y of t is equal to, well, 0 times a plus e to the 5t times b. Right, and I put in that 0 just to help in recognizing this as xy equals the product of e to the 2t, 1/3 e to the 5t, 0 e to the 5t. times the vector little a, little b. Right, so I'm going to write that as the vector v is equal to m of t times the vector c. So here, this is the matrix m of t, and then this is a matrix, it's not a matrix, it's a column matrix, so a vector made up entirely of constants, right? Constants a and b. You could also write this as a times the first column of the matrix, so e to the 2t0, plus b times the second column of the matrix, 130 to the 5t and e to the 5t. Right. So if you call the first column of the matrix v1 of t and the second column of the matrix v2 of t, then we have a times v1 plus b times v2. Right? So this is the general solution. You get to pick these constants, and then this gives you the solution. So the key facts are that the columns of m of t, right, this v1 and v2, both solve the original equation, v prime of t is equal to a times v of t. And the set containing v1 of t, v2 of t is linearly independent. Right? This is easy to see directly. Right? To say that this set is linearly independent is the same as saying that the only linear combination of these two vectors that it's equal to the 0 vector is the linear combination where both coefficients are equal to 0. And that's really easy to see directly, because if you have a linear combination of these two vectors equal to 0, then, well, by looking at the second coordinate, you see that this coefficient b has to be equal to 0. And then once the coefficient b is equal to 0, if this is equal to 0, then the coefficient a has to be equal to 0. So the only linear combination of these two vectors that's equal to the 0 vector is the trivial one, where both coefficients are equal to 0. So that's easy enough to see directly, but you don't have to see it directly. You can also take the determinant of the matrix, right? Remember, this matrix is called the fundamental solution matrix, and its determinant is called the Wronskian, right? So this would be the Wronskian of the solutions v1, v2, right? And in this case, the determinant of this matrix is e to the 7t, and that's not equal to 0. Because it's not 0, that means the columns have to be linearly independent. Okay, so that's what happens in this particular case. But in fact, this is what happens in the general case. Something like this is true. Right? The difference is that in this case, we were able to just solve one equation at a time, whereas in general, you have to do something different. Right? So let's go back to considering dv dt equals a of t times v, where v is going to be a vector with n coordinates, and a is going to be an n by n matrix. Right? So first, a linearly independent set of n solutions, v1 of t up to vn of t, is called a fundamental set of solutions. So in our example, right, this set would be e to the 2t 0 and then 1/3 e to the 5t e to the 5t. This is a fundamental set of solutions. But it's not unique. Another one would be, for example, take minus e to the 2t 0 and then take e to the 5t and 3 e to the 5t. Right? That would be another perfectly good fundamental set of solutions. Right? Then a fundamental solution matrix for this equation is a matrix M of t whose columns make up a fundamental set of solutions. So in our example, M of t e to the 2t 0, 1/3 e to the 5t e to the 5t is a fundamental solution matrix. Right? It's worth pointing out that it's also not unique. Right? Another one would be take this other fundamental set of solutions and use those as columns. Okay, next. Linear independence of this set of solutions that's equivalent to the Wronskian v1 to vn, right, which by definition is the determinant of the matrix M of t being not equal to 0, and so it's also equivalent to this matrix M of t being invertible. Right, in our example, right, the Wronskian of the two solutions we used, right? It's the determinant of this fundamental solution matrix we found was e to the 7t, right? And so in particular, not equal to 0. Right? And then what makes everything here deserve the adjective fundamental is that the general solution of the equation dv dt a of t v is c1 times v1 of t plus c2 times v2 of t plus dot 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 plus cn times vn of t, right? So a linear combination of v1 through vn with these constants c1 through cn arbitrary. Another way of writing this is the matrix M of t times a vector made up entirely of constants, c1 through cn. So you could write M of t times c bar, right? Well, c bar just denotes this vector of constants. Right, so in our example, the general solution was e to the 2t0, 1/3 e to the 5t, e to the 5t times a vector of constants, a and b, right? So exactly M of t times c bar. Okay, so now suppose you want to solve an initial value problem, right, where you have dv dt is equal to a of t v bar, and then you impose that v bar at t naught is the vector v naught bar. Okay, so from our previous bullet point, we know the solution has the form v of t equal to the fundamental solution matrix times some constant vector. And so we just need to find the correct constant vector using the initial condition. Right? Just as we're used to. You find arbitrary constants for the general solution, and then you determine those constants by using the initial condition. In this case, since we want v bar of t naught to be, right, on the one hand, we know it's m of t naught times the constant vector c. On the other hand, we want it to be equal to v naught. Then we can just solve for c. The constant vector c should be m of t naught inverse times v naught bar. Okay. So the solution of the initial value problem is v bar of t equals m of t times m of t naught inverse v naught bar. Okay, and the final thing I want to note is that m of t itself satisfies the matrix valued ODE. Take the derivative of m with respect to t, and that's the same as a of t times m. Right, that's easy to see. Right, the derivative of m with respect to t would be, right, remember that M is the matrix whose columns are V1 through Vn, right? V1 through Vn making up a fundamental set of solutions, right? So if you want to take the derivative with respect to t, then the first column would be V1 prime of t, right? The second column would be V2 prime of t, and so on. Right? But each of these columns satisfies the ODE we started with. So V1 prime is equal to A times V1. V2 prime is A times V2, and so on. But it turns out that if you have a matrix A and you multiply a matrix with columns V1 up to Vn, what you get is exactly the columns A of V1, A of V2, and so on up to A of Vn, right? So, and then this is exactly A of t times m. Okay, so with that discussion of the homogeneous linear case out of the way, let's state the variation of parameters theorem. So this term says that if m of t is a fundamental solution matrix for the homogeneous equation, dv dt is equal to a of t times v, then the solution of the initial value problem, where you have dv dt is equal to a of t v plus a forcing term, right? So this is a non-homogeneous equation, and we have an initial condition is given by, and then we have an explicit formula for it. V bar of t is going to be m of t times the integral between t naught and t of m of s inverse times f bar of s ds plus m of t times m of t naught inverse times v naught bar, right? So recognize this as being the solution to the associated homogeneous problem, and then this is a particular solution to the non-homogeneous problem. Okay, so let's prove this. Okay, so let's start just like the other variation of parameters, the one we did for scalar valued differential equations. So we start by noting that the general solution of the associated homogeneous problem is, let's call it V sub h for homogeneous, m of t times c bar, where c bar is a vector of constants, right? Just like in the scalar valued case, when the parameters in the variation parameters refers to these arbitrary constants, right? So here, to vary parameters, means that instead of thinking about c bar as a vector of constants, we're going to allow it to depend on t. And so we will consider V sub p for particular given by m of t times c of t, right? So now this vector that used to be of constants is now allowed to depend on t. So what we need to do is find a particular vector c of t so that V sub p of t satisfies the non-homogeneous equation. Okay, so to do that, let's compute the derivative of V sub p. Okay, so it's given by a product, the matrix vector product, but the Leibniz rule still applies. And this is going to be m prime of t times c of t plus m of t times c bar prime of t. Okay, now our last bullet point up here was that m prime is equal to a times m. So this is a of t times m of t c bar of t plus m of t c bar prime of t. Okay, and notice that we ended up with m times c bar, and m times c bar is exactly v sub p. So I can write this as a of t v sub p of t plus m of t c bar prime of t. Okay, and we want this to equal a of t vp of t plus f of t, right? That's the equation we want. We already have v prime is equal to this. So just comparing, this term is the same as that term. So all we need is for this to be equal to this. Okay, but M is an invertible matrix, so this just says that C bar prime of T is equal to m of t inverse times f of t. Okay, and now I'm going to integrate both sides, but instead of just taking the antiderivative, I'm going to do a definite integral because we're trying to solve an initial value problem. So let's take the definite integral between t naught and t. So on the left-hand side, I'm going to get c of t minus c of t naught. And on the right-hand side, I'm going to get the integral from t naught to t of m of s inverse times f bar of s ds. Okay, so substituting this back in, we have that v sub p is m of t times c bar of t, but we've found c bar of t, so this gives us m of t times the integral from t naught to t of m of s inverse f bar of s ds plus m of t c bar of t naught, right? So it's because we're applying to c of t, so this c of t naught has to go to the other side. Okay, so finally, let's look at our initial condition. We want v of p at t naught, right? Which if you plug in t naught to this right-hand side, you get the integral from t naught to t naught, so that's just 0. And so this is the only term that remains. Right? And we want this to be equal to v naught. So that tells us that c bar of t naught needs to be m of t naught inverse times v naught bar. And so altogether we have vp of t equal to m of t times the integral from t naught to t m of s inverse f bar of s ds plus m of t naught inverse v naught bar, like we wanted. We can appeal to the existence and uniqueness theorem to see that this is the only solution. Okay, so variation of parameters in this case was very simple, right? Partly that's because we just had a first order differential equation, even if it was vector valued. As a remark, another way of stating this, so if you don't want to work with initial value problems, is to say that a particular solution of the non-homogeneous equation is given by vp of t equal to m of t times, let's call it w of t, where w of t is an antiderivative of m of t inverse times f of t dt, right? So we don't write the general formula in the initial value problem like this because it can be confusing to have the m of t outside the integral and m of t inside the interval integral, it might look like they cancel, when really what's going on is something like this, where you have m of t outside the integral, and the m inside the integral really depends on whatever dummy variable you're using to integrate, right? So this is m of t and this m of s. And so this m of t does not cancel with this m of s inverse. In any case, that's how you find a particular solution, and then the general solution of the non-homogeneous equation is, as usual, given by the sum of a particular solution and the general solution, right, m of t c bar, of the associated homogeneous equation. Okay, so let's go back to the example we worked out at the beginning of the lecture and add a forcing term and see what this formula looks like in practice. So suppose we wanted to solve dv dt is equal to the matrix A given by 2, 1, 0, 5, v var, plus, and let's take a simple forcing term, just a couple of exponentials, e to the minus t and e to the 3t. So AV plus F bar. Right, so we know from the beginning of lecture that a fundamental solution matrix is given by this one, for example. This is fundamental solution matrix for the associated homogeneous equation. Okay, so if we want to apply the formula, we need to compute the inverse. Okay, so there's a trick to computing the inverse of 2 by 2 matrices. It makes it very quick. So you just do 1 over the determinant, which in this case is e to the 7t. And then these two entries, the ones on the diagonal, change places. The anti-diagonal matrix entries change sign. So here we're going to have e to the 5t, 0, minus 1/3, e to the 5t, and e to the 2t. Okay, if we multiply in this determinant, we end up with e to the minus 2t, and then minus 1/3 e to the minus 2t, and then 0 and e to the minus 5t. Okay, and so we have, if you have this m of t inverse times f bar of t, so this would be this matrix, e to the minus 2t, 0, minus 1/3 e to the minus 2t, e to the minus 5t, and then the vector f is e to the minus t, e to the 3t. So let's multiply this out. This would be e to the minus 2t times e to the minus t plus minus 1/3 e to the minus 2t times e to the 3t. And then down here, we'd get 0 plus e to the minus 5t times e to the 3t. So if we work that out, this first term gives us e to the minus 3t. And then this gives us minus 1/3 e to the t. And then this gives us e to the minus 2t. Right? So then w bar of t would be the antiderivative of m of t inverse f bar of t dt. So this would be an antiderivative of this vector So when you have a vector made up of functions of t, and you're integrating with respect to t, all you do is take the integral in each coordinate separately. So we end up with another vector where I'm just going to integrate the first coordinate and get minus 1/3 e to the minus 3t, and then minus 1/3 e to the t, and second coordinate minus 1/2 e to the minus 2t. And so our particular solution, Vt of t, right, this would be m of t times w of t. So this would be e to the 2t 0, 1/3 e to the 5t, e to the 5t times w of t, which is this minus 1/3 e to the minus 3t minus 1/3 e to the t, and then minus 1/2 e to the minus 2t. So that gives us e to the 2t times minus 1/3. Pull out the minus 1/3. So minus 1/3 e to the 2t times e to the minus 3t plus e to the minus t, e to the t. And then here plus plus 1/3 plus 1/3 times minus 1/2 is minus 1/6 e to the 3t. And then in the second coordinate, we would get minus 1/2 e to the 3t. Right? So altogether, that would be minus 1/3 e to the minus t. And then let's see, we have e to the 2t times e to the t is e to the 3t. And so I have minus 1/3 here and minus 1/6 here. So altogether, that's minus 1/2 e to the 3t. And then here, minus 1/2 e to the 3t. This gives us the particular solution we were looking for. Using the formula, it might be worth checking directly that this worked. So the claim is that this is a particular solution So let's compute VP prime of t, right? Just differentiate each coordinate. So here I get 1/3 e to the minus t minus 3/2 e to the 3t. And then the second coordinate, I get minus 3/2 e to the 3t. Right, on the other hand, if you do a times VP, so a was 2105. And if you multiply this particular vector, so minus 1/3 e to the minus t minus 1/2 e to the 3t, and then here minus 1/2 e to the 3t, right? We're going to get minus 2/3 e to the minus t. And then, let's see, 2 times this plus this. So it gives us minus 1 times e to the 3t minus 1/2. So altogether, that's minus 3/2 e to the 3t. And then down here, we end up with minus 5/2 e to the 3t. Okay, and so then when you do a of VP plus f bar of t, you have this vector minus 2/3 e to the minus t minus 3/2 e to the 3t minus 5/2 e to the 3t. And then to that, you add the vector f, which is e to the minus t and e to the 3t. So altogether, if I have minus 2/3 plus 1, that's 1/3 e to the minus t, and then minus 3/2 e to the 3t, and then down here I have minus 5/2, and then I add 2/2, that's minus 3/2 e to the 3t. So, excellent. This matched this. So we did indeed find a particular solution, right? Verifying that in this case, the formula works. So the general solution is V of t equals the particular solution plus the general solution of the associated homogeneous equation. So that would be our particular solution minus 1/3 e to the minus t minus 1/2 e to the 3t minus 1/2 e to the 3t plus the fundamental solution matrix times a vector of arbitrary constants. Okay, and we'll stop there and pick it up from there next time.